Welcome to section 14.4. This is green theory examples. So let's look at the vector fit. Let's look at the integral over the curve C of f dot n ds for the vector field f x plus y comma x minus y on the curve from the point 3 comma negative 2 to 3 comma 2 given by r of t equals 3 comma the curve defined by 3 comma t on t equals element from negative 2 to 2. So as we see this, note that C is not a closed curve. We're starting and ending at different points, so we cannot use properties of closed curves. So when we're looking at our vector field here, so f dot n ds is equal to C, we can do m g prime minus n f prime dt. This is again for a two-dimensional case. We'll extrapolate up to a three-dimensional case in later sections. So this is when we substitute in our vector field f, so m evaluated at the x plus y, so I get 3 plus t times g prime, which is 1 minus 3 minus t times f prime, which is times 0, dt, and our t goes from negative 2 to 2. So then I get the integral from negative 2 to 2 of 3 plus t dt, which gives me 3t plus 1/2 t squared, evaluated from negative 2 to 2, which gives me 6 plus 2 minus negative 6 plus 2, which gives me 12. Our second example, let's find the area of the region enclosed by the curve C by computing the closed interval, or the closed integral f dr for the appropriate vector field where the curve is 4 cosine t, 3 sine t on t equals 0 to 2 pi. This is a curve and this is an ellipse. So let's look at the curve C of f dr. Let's use Green's theorem here. And so RDA. So we can look at an appropriately chosen field. So our curl of f dotted k dA. So this is Green's theorem. And so when we're looking at this, let's choose, since we're dealing with sines and cosines in our curve, let's let our vector field f be equal to negative 1/2 y comma 1/2 x. So anytime you have a cosine sign in this sort of format, this choice of a vector field is often appropriate. Not always, but it's always a good choice to start. So if this is our vector field f, then in terms of our x and our y in our curve, we have negative 3/2 sine of t, comma 2 cosine of t. So then our vector field here is given as 0 to 2 pi as our bounds of negative 3/2 sine of t, comma 2 cosine of t, dotted with our derivative of our curve for sine of t, comma 3 cosine of t, dt. So 0 to 2 pi. We get negative 3/2 times 4, so that gives me 6. And then the sines multiply to be sine squared, plus another 6 cosine squared t dt. The sine squares and the cosine squareds cancel, so we get 0 to 2 pi of 6 dt, which gives me 12 pi. So the area of this ellipse is equal to 12 pi. So as always, if you have any questions, feel free to let me know.